So I just want to go back to your question. It is, yes, all this is doable in Stata. Um, and Stata is it's a bit more versatile, in fact, than R when it comes to SEM
Oh, yeah,
modeling,
that'd be great.
primarily
Thank you.
because you can
Thank you.
use many of the post hoc um, post hoc kind of just baked in things that you can do with Stata, like marginal estimates, pairwise comparisons, ANOVA contrasts, all that stuff that really help you better interpret and visualize rather than just report beta coefficients and confidence intervals. All that is much easier to do at least in my opinion, much easier to do in Stata than it is to do in R. However, R is, builds, I say easier to do because it's boxed in. R, on the other hand, you need to have kind of that, initial getting used to the software, being able to navigate across
Yeah.
packages and so on and so forth.
Mhm.
So that's why we're here for. When you get into these things, you just reach out to me or Bree. I'm sure we can talk about how best to approach this.
Okay, thank you.
Yep. Okay. So are we ready to go? Okay. So I titled this "Working with Latent Variables," but I think I'm going to talk beyond just latent variables. So I have a lot of slides, and what I'm trying to do is move back and forth between things that we know and we've dealt with, the easy stuff, so that we can make connection to the relatively more complicated stuff. So what I'll do is I'll start with some observed variable techniques, and I want to link them to some standard methods that we've all used. So that's path analysis. I will then go into the SEM version of these techniques, particularly focusing on a subset of models within SEM called confirmatory factor analysis. And then what that will allow me to do is jump into kind of SEM formulation of something that is slightly more complicated called growth trajectories. So I'm going to do both cross-sectional stuff and I'm going to do longitudinal stuff. Before I go into growth models, what I'll do is potentially, because some of you have worked with those techniques before, I'll just present the multi-level, the standard multi-level, the mixed modeling framework of doing things, because it's more familiar to some of you. And then this way we can relate some of the terminology to SEM. And then throughout, I'll try to kind of, show some applied examples using data from the HRS, and we'll make the code for reproducing some of these results available. Then I'll finish briefly listing some of the complications, because most of the things that I'm going to talk about today assume that both the mediators and the outcomes, as well as the manifest variables, the observed variables, are all continuous, and that is kind of, most of the actual real life work that we do does not focus on continuous variables. It focuses on categorical kind of count, et cetera, et cetera. Does that sound like a reasonable plan to move through things? Yes. And here's the other thing. I don't want to lecture. So stop me, ask questions. Like this is for you. I think Bree and I know this stuff, inward and outward. So this is for you. If there's something that you want to relate to some stuff that you're doing, I'm more than happy to just stop and talk about that. So why do we talk about SEMs? Well, SEMs is a powerful, flexible technique, and it encompasses a wide variety of models. Among them is the one that we're going to start talking about today, which is confirmatory factor analysis. If you understand that, you understand potentially everything else. One of the primary draws of working within the SEM framework is that you can do everything that you do with observed variables, and you can extend that to what we call latent variables and structures to test latent variables. So you can do things like a simple t-test using SEM techniques. Then you can do path analysis. You can take that path analysis and apply it to a confirmatory factor analysis on some outcome. That outcome could be a manifest variable, an observed variable, or it could be a latent variable. You can take the same principles here from C, and then just extend them a little bit, and you get to longitudinal analysis. Then once you know kind of the basics of longitudinal analysis, you can take that and apply some kind of a path analysis framework to that and extend it so that it's longitudinal analysis that have either covariates attached to it or distal outcomes that you wanna connect to it. There are many more things that you can do with this. But let me start with the simple stuff. Path analysis, I think most of us have done work using path analysis, and sometimes we don't realize that we're doing path analysis. Regression modeling is really path analysis that restricts some of these path to zero. Basically, if you know how to do regression, you know how to do path analysis. Path analysis are just manifestation of conceptual and theoretical models. It's a system of, in this particular case, linear regressions. So from linear regression, kind of univariate linear regression, we know how to estimate B, for example, right? B is nothing but the it's the covariance of education and parental education over the variance of parental education. We can extend that to estimate what C and A are. This is just moving from univariate regression to multivariable regression. In this case, you have two x's that are being regressed on the y in this case being cognition. We can add things to this that are kind of the more interesting things that scientists do, which is go from the sample to the population by estimating inferential statistics. If you're using just a software, these things come standard with the software, but you can complicate that and use resampling techniques because the standard way of calculating inferences assumes certain things that, like normality, that are probably inappropriate. And the good thing is that nowadays, with the advancement in computing and in software, all this can be done with a couple of clicks. So it's nothing really major. This simple example that you see here can be complicated a lot by adding a lot of other covariables. You can add multiple mediators. You can have connections between residual variances if the structure is not, you can complicate the structure of connections between residual variances, et cetera, et cetera. But the principles, if you know how to do this, the principle for solving this problem actually holds. So this is how we usually approach a regression problem. Here, we say that we assume that mother's education and father's education are linked to cognition. And then controlling for age. We might also hypothesize that there's something that complicates this relationship, is that education is in fact what drives cognition rather than mother's education and father's education. So once we include education into the model, how many of us have talked about attenuation or accentuation of effects? Really, the attenuation, accentuation, mediation, in my mind at least, these are omitted variable problems, right? You don't account for this, and therefore you're going to have an overestimate of what this D prime and E prime is. Once you include education in the model, right, you estimate C, and then D and E kind of revert back to what their actual, causal or associational values are with cognition. All right, so scenario one, we've done that. We call it hierarchical regression. We call it sequential adjustment for covariates, et cetera, et cetera. Now, this scenario one can be slightly more complicated through path analytic frameworks. Now we're moving into actually testing theoretical models rather than just running regressions. So you can assume that the entirety of the association between mother's education and father's education and cognition runs through achievement, the educational achievement of the individual, rather than being directly associated with cognition. So in this particular case, what you're doing is restricting the parameter linking the association between mother's education, father's education, and cognition to zero, and assuming that it's this path, an indirect path, that really controls the association. You can also say, so in this particular case, you're assuming that these what we call direct pathways are completely explained by the indirect pathway. However, that might not be the case. And so you might assume that some of the association goes through education, and part of it is also a direct link between mother's education and cognition, father's education and cognition. just by the way, scenario 1, which is the standard regression model that we all are familiar with, and scenario 3, just because both are based on the same variance covariance matrix, they're the same. So that you will get the same model fit across these two formulations. However, scenario 2 and scenario 3 are different. They have different degrees of freedom, and therefore you can use standard fitting techniques to kind of compare the two and reach a conclusion about what model kind of matches the data better. And we'll talk a little bit about what some fit estimates, but I'm not going to go too much into this. Any questions so far? I know I tend to talk a little fast, but interrupt me again, stop me. Okay, I just want to
Waseem, I just wanted to emphasize one thing that you said, because I haven't heard it phrased in that way very as often as I should have, but the viewing the omitted variable problem and sort of viewing sort of not accounting for the mediator or not accounting for the moderator as this omitted variable problem. And I really, one of the things I love about path analyses or other ways of visualizing our sort of structure of problems, or sort of, is that this allows you to sort of say like, well, is there really nothing going? Is there really nothing, no
Exactly.
path here, right? And so I guess I just wanted to emphasize that, because I haven't, that framing, that term of omitted variable is in terms of how it relates to path analysis. I haven't heard that linked as closely as you just did it there. And I just wanted to emphasize that point.
And I completely agree with you, Bree. In fact, I think the one thing that path analysis really forces me to do is to, it forces me to think from a more theoretical perspective about relationships rather than just throwing covariates at the model. It makes you aware of what is happening in your in terms of the relationships that you're trying to assess or test. And I think we should all start by having a conceptual model and then making sure that what we're test relate back to that conceptual model. Now, I think this is one of the at least my kind of relation to path analysis. That's I think the really the strength of this technique.
100% agree.
Okay. So what I'm showing here is how you go from this to this. And the main thing that I want to emphasize here is that the interpretation is standard regression interpretation, right? What you see is beta coefficients, potentially kind of more complicated sets of equations, and that's just a reflection of the model that you're testing. What the software usually spits is the estimate, the beta coefficient, the standard error, the probability, the p-value associated with that. And then an easier way to interpret some of these models, instead of looking at kind of metric associations, is to look at standardized association. This presents some complications if you have kind of a binary covariates or a categorical covariates that you're linking to a continuous outcome, because what is the standardized, how can you standardize sex, or how can you standardize race, or whatever. So there are different ways by which you can look at this, but in this case, we're lucky in that all the covariates and the outcomes are continuous. So basically what you see here is that the way to interpret this is a 1 standard deviation increase in age is associated with about 1/3 of a standard deviation decrease in cognition. What this allows you to do, looking at standardized versions of things, is also to compare kind of the effect size, right? So you see that maybe this is a little stronger than this, and then what you see here is that mother education, father education are significantly associated with cognition, but that association is relatively small. This is where things get exciting, in that the direct associations are small. However, the total effect of maternal education and paternal education are much larger than the actual direct effect. And this is something that you have to estimate kind of using some of these some extra coding into the model, but you can get an estimate of this, and you can get inferential statistics associated with it, the standard errors, and then p-values associated with that standard errors. So what you see is that if you compare the direct effect to the total effect, you'll see that the total effect is much bigger than the direct effect, primarily because a lot of the association linking maternal education to cognition goes through the individual achievement in terms of education. All right. So if you were to estimate maternal education, paternal education without accounting for education, this is what you get: 0.156 and 0.125. Once you control for education, then these two numbers are reduced to 0.0054 and 0.043, meaning that, right, the way you interpret it from a regression perspective, you say education explains the association between mother's education, father's education, and cognition. From a path analytic perspective, however, this is a relationship of interest. The indirect effect is something that is of value to you to interpret. Okay, I've spent too much time talking about manifest variables. Let me switch a little bit to the latent variables. So if you know manifest variables, getting what latent variables do is relatively straightforward, right? What we've done in the previous models is assume that cognition, for example, is an observed variable, right? Basically, the way it was measured here is through the TICs, which is two indices of memory, serial sevens and backward counts, and then the mental status. And then basically we added them, we summed them up, and then we used that as the outcome. So if we believe, however, that these variables derive from an underlying structure that cover cognitive capacity in an individual, potentially all these variables are not equally connected to that unmeasured variable that we call cognition, right? So we can reconceptualize this and argue that the interrelationships between these X variables, right, exist because they are caused by this unmeasured factor. So we're going to use these information from these variables collected through what we call manifest, and attempt to infer information about the latent variable that we believe exists, but we have not measured. This is what we call the factor. Okay, so let me. So the mechanism by which we do this, and I don't want to go too much into the math here. The mechanism by which we do this is what we call this confirmatory factor analysis. The same principles that were just stated apply to kind of generate more complex models, if you want, and I'll show you what I mean by that. But latent variables, the one thing to kind of get out of this is they're representations that are not directly observed. They are inferred. I like to think about it as a missing values problem, right? You have this, you have this, you have this, you have this, you have this. You have some assumptions about what the distribution of this looks like, and you want to fill in, right? You don't have any values for this, and you want to fill in the information into this based on the the variance covariance matrix that we have for these guys. So the problem then is to take these set of items that we observe and make inferences about something that is unobserved. So how do we do this? It's again, as I said, it's based on some hypothesized assumptions about what the structure looked like. So it could be one latent factor, it could be two latent factors, it could be three latent factors. Once we venture that informed guess about what we think exists, then our job is to compare how close these hypothesized structure are to the actual data. And we do so by fitting across these multiple formulations and testing the fit of these models, then reaching a conclusion about which one of these models fits best. So here I moved from cognition to give you an example about SES. These are the manifest variables that we have measured in the data. So we have things like assets, we have education, we have someone's assessment of where they are on the work ladder, and then we have mother's education and father's education, right? We can think of all these manifest variables as underlying an unmeasured factor that we call SES, or we can think of this as two separate latent factors, one that is adult socioeconomic achievement and one that is childhood socioeconomic status, right? So you can fit these two models and then compare them. The estimation of the model parameters, this is the math that's included here, which I'm not going to go to, is done usually by minimizing what's called a criterion equation. As we engage in this process, we should always be mindful of the issue of identification. This is a problem that people don't think about that often. And identification is nothing but realizing that you have to have enough pieces of information in your data that allows you to estimate the structure that you want, right? So if you don't have enough information in your actual data based on this variance covariance matrix that you have, then potentially you're restricted in the number of factors that you can estimate. I talked about models of fit. The most common way of assessing fit is by looking at the chi-squared goodness of fit, which is, it just compares the model variance covariance matrix to the population variance covariance matrix. And all that really is you're basically imposing constraints on these interrelationships that exist between the manifest variables. It's nothing like that. Some restricted to 0, some not restricted to 0, and then comparing the impact of restrictions versus non-restrictions on the overall fit of the model. If you're into SEM, you'll know that this is a very controversial thing, whether you should look at the chi-square goodness of fit versus you shouldn't. And chi-square tend to be limited. It's very kind of sensitive to sample size. It's also loaded with assumptions, one of them being multivariate normality. Although I should say that there are many other kind of formulations, corrections that have been suggested so that you can overcome that. There are other things that are relative fit indices. So these will allow you to assess, and those are derivations from the chi-squared measure. They allow you to kind of see the fit of the model. Things like the RMSE and the CFI. There are things that are in this particular case, comparing across models that are really, really useful to compare nested models. These are things that you look at to see if model 1 is better than model 2, model 3, model 4, et cetera, et cetera. So the AIC and the BIC, as I mentioned, there are sample corrections for those because they tend to be a little sensitive to sample size. So let me take this from kind of the theoretical level to a more applied level. So what we've done here is assume.
I'm so sorry.
Yeah.
It's actually about the previous slide. So with the different goodness of fit or model fit assessment measures, sometimes I feel like what one test will say is the sort of preferred model is different from what another test will say, like RMSEA is different from AIC versus BIC. So what do you do in that situation? Do you go back to what you theoretically believe is the best model? Or is there literally like one fit assessment that's superior to the others? I know that's like really general, but you get what I'm saying?
Was there another question?
No. I was just trying to make sure like my question was clear, just like inconsistencies in terms of which test says what is the preferred model.
And this is a very, very interesting question. I wish I had the answer to that. As you probably know, there's a big debate about what is the best fit statistic to assess a model. I think what you want to do is make sure that all the information are pointing in the same direction, right? Now, as you in reality, what you find in many cases is that's not always the case. So sometimes you might get kind of a great RMSEA, a relative fit index, which is driven by the chi-squared fit statistic, but you can get a difference between where the AIC and the BIC are pointing in terms of which model to choose. And so for that, I think then you have to kind of ground yourself in the concept and the theory and make the best out of it. There's, every day people publish about doing simulation modeling of these different fit statistics to show what would happen, for example, to these fit statistics when you have some violations of assumptions. And I think that's the literature that you wanna stick to. But as you alluded, is there a straight way to adjudicate between these? And the answer is it depends. And that, at least that's the best answer that I can give. We just published a paper where we had clearly the AIC and the BIC pointing in one direction, but other fit indices were saying, well, maybe you should look in a different way. And we just had to lay out our cards and say, this is what we have. This is how we went into this, thinking based on previous literature. And this is how, we decided to settle. Okay, and I can send you some really classic papers published about 15 years ago now by Mitan and a couple of his graduate students about which of these measures to use and which kind of to trust more. And they have also kind of simulation papers that they've also published on this stuff. So I can send you that.
Thank you.
Okay, so this is, again, going back to the question is what you're seeing here, in addition to kind of just what the factor loadings look like for the one factor solution versus the two factor solution, what you're seeing is these fit indices that you're going to be used to say, this is the structure that I'm going to adopt. This is the structure that I think fits the data better than a different structure. So what you see here in the table is, first of all, different ways by which the models were estimated. So whether through maximum likelihood or weighted least square. I'm going to focus on the weighted least square for one factor versus the weighted least square for two factors. And what you see here is the RMSEA, the CFI, the TLI, the RMSEA, the SRMR, and then the model fit statistic, which is the chi-squared statistic. And so if you look at the kind of the totality of these, you get to the conclusion that the two-factor model estimated in the weighted least square is potentially the best fitting to the data. It has the highest CFI, the highest TLI, the lowest RMSEA, and the lowest SRMR. Although if you kind of compare this to the thresholds that are established in literature, you'll see that this is higher than the 0.05, that is 0.005. That's usually adopted as a kind of indicative of good fit. And this is primarily because this was just an example rather than actually theoretically driven formulation of a CFA. So if you were to look at the data and the fit, what you will see is that I'm going to adopt this as my solution, that we have two different factors, SES1 and SES2, SES1 being adult socioeconomic status and SES2 being childhood socioeconomic status. Childhood socioeconomic status is underlying two variables, the mother's education and the father's education, whereas the adult is kind of based on assets, accumulated assets, number of school years, and assessment of where the person is on the work ladder. You can actually do a comparative fit testing, and what this shows you is that the p-value is rejected for this model relative to this model. So you have a p less than 0.05, which means that this is better than this. The two factor is better than the one factor model. I'm not going to go into the factor loadings. Most of us know what these are, but if you have any questions afterwards, do ask them. So we know what CFAs look like. The next kind of logical step is to kind of think back on the path analyses that we've discussed at the beginning of this and say, now that we know how to measure latent variables, how to measure factors, unmeasured factors, what we can do is, once we do that, we can relate them to some outcomes, or we can have them being predicted by some other variables, whether they are manifest observed variables or non-observed latent variables. So again, what you see here kind of is the same, evolution in thinking about model fitting that we talked about when we talked about path analysis. Here, we're thinking that childhood socioeconomic status influences cognition, controlling for age. Remember, we said there's a missing, variable problem or unmeasured variable included in the model problem. So we think that this C prime is actually explained by adding adult socioeconomic status. We can fit this model, and the assumption is that once you control for this, the effect of C prime is going to be rendered into C, potentially either attenuated, reduced, or accentuated, meaning rendered more stronger. We can also say that, this is potentially not the right way that the theory works. In fact, what we think is going on is that childhood socioeconomic status influences adult socioeconomic status. So there's a connection, right? A causal connection between childhood socioeconomic status, adult socioeconomic status, and cognition. So you can potentially move from the scenario 2 to scenario 3. And then you can, as we did with path analyses, you can estimate indirect effects and total effects, and then make substantive statements and judgments based on those. I'm not gonna fit all 3 models, but I'm going to show you what fitting that third scenario looks like, right? So now you have childhood socioeconomic status influencing adult socioeconomic status, and both influencing cognition, controlling for age. As I said before, this becomes just a standard regression interpretation. So what you see here is this is the links between the manifest and the latent for adult SES, the manifest and the latent childhood SES. And then all these are just regression estimates, right? So you see that adult SES, a 1 standard deviation increase in adult SES leads to about a half standard deviation increase in cognition. Childhood SES has, once you control for adult SES, has relatively a relatively small direct effect, right? But that's not the whole story, right? Childhood SES has both an indirect effect on cognition as well as a total effect on cognition. And if you take those into consideration, then you can make better, right, as we said before, better statements about how the kind of the flow of effects, of causal effects, go from childhood to adult cognition. All right. The one thing that I'm not showing here is estimates of residual variances. I'm not showing them because the interpretation of those is standard, again, based on regression. So what you see is how much of the residual variance stays or remains after you control for added elements into the model. And that's something that potentially most of you have done in the past. Before I make the switch to longitudinal stuff, are there any questions? Anything that you've been doing in your work, kind of that potentially this what we presented now would allow you to extend, and you want to ask questions about anything that's not clear?
Yeah, I have a question, Waseem. This is Kathleen. I was wondering if you could talk a little bit more about the nested models. Around the time Christy brought up her question, I was like, okay, I'll just save mine to the end. When you say nested models within this latent variable modeling framework, what do you mean?
Okay, so if you think about this, is probably easier to relate to than the SEM way. So scenario 2 and scenario 3 are what you call nested models, right? And the main reason you call them nested models is because you're making direct assumptions about some elements of the variance covariance structure, right? In scenario 3, you're assuming that this pathway exists and is estimable. It's not equal to 0. It's not null, right? You do the same thing for E. You assume that the effect of father's education on cognition is also estimable. So it's not equal to 0, right? Mm-hmm. In this case, in scenario 2, you're forcing those pathways to be equal to 0, right? Mm-hmm. So this has more degrees of freedom in this, and you can compare the chi-squared fit for this model and say, well, the chi-squared fit points to this model being a better model than this. Therefore, you reach the conclusion that forcing pathway D and pathway E to be equal to 0 is not theoretically valid.
Okay.
Okay.
So that makes, because for me, I was stuck on just thinking in terms of the multi-level way of thinking of nested models. And so this is clearer for me. Thank you.
Sure. And let me just kind of extend that a little bit to these 2 models. These are also nested models, right? Again, this model here and this model here have the same variance covariance structure, right?
Mhm.
but at least kind of when you don't have any constraints imposed on it. The main
Mhm.
difference is in terms of constraining some of these loadings, right?
Mhm.
So
Mhm.
here in this model, you're constraining this, this, and this to be equal to 0. And you're
Mhm.
constraining this and this to be equal to 0,
Mhm.
right? And so basically what you want to do is estimate this, look at the chi-squared, look at the degrees of freedom between these two, and
Mhm.
kind of do a chi-squared difference test to
Mhm.
see which one fits
Mhm.
your data better.
Okay,
That's also another example of a nested model.
thank you.
Okay, great questions. And in the code that I'm going to post and share with all of you, I have some code on how to do this if you're not familiar with the process. All right, so I'm going to we have about 20 minutes, so let me switch to change. Right, so far we've been talking about just cross-sectional associations. So I assume that many of you have an interest in examining change. And in this case here, we're looking at change in at least, as an example, let's say change in cognitive performance over time. Okay. So looking in this particular case, what we're seeing here is scores of one individual over 5 time points. Really, the 5 time points, when we're looking at change, the individual 5 points are less interesting to me than to find a summary that underlies these scores, what we call the trajectory of that individual. And in this case, the trajectory that I'm seeing here, at least that I forced on this model, is a linear trajectory in kind of regression terminology. And what is a linear trajectory? This is this is the best linear fit, the expected value really that minimizes those deviations, the errors that exist around that line. This trajectory, like with any other regression that you've done in the past, it could be summarized by 2 elements, right? It could be summarized by where you start and how you change, which we call the intercept and the slope. The intercept being the baseline value, the value at time 0, and the slope is the rise over time. In this case, we assume that things are increasing, so you're gaining over time. In other instances, it could be decreasing or unchanging, and that is based on this is based on data rather than just theory. So, well, not theory, just the example that we're giving. So the residuals of these deviations around the expected values, the variance of these residuals is what we call, when we're looking at change models, is what we call within person variations, right? These are variations that are not explained by the time indicator, right? So all this is something familiar. You know what it is. Now, of course, the data usually includes multiple individuals, and each has their own set of observations. So we can, as a result of that, characterize each one of these trajectories. And so the graph that you see here includes 8 individual trajectories. This is kind of a dummy data set. And our goal often in change models is to summarize these trajectories, right, or curves. The way we do so is by, for each one, we extract a mean and then a deviation measure around these means, right? So because each one of these trajectories is a linear trajectory, right? So basically it could be summarized by 2 elements, as we said, the intercept and the slope. So a good summary of these trajectories would include an average of these measures, right? An average of the intercepts and the average of the slopes. And then we can also, in addition to the average, we can also look at deviations from these averages. Now, if we plug in these values to the individual level model and rearrange, right, you see that the math here, this is what is the mixed level equation that some of you have seen in the past. Okay, so just to kind of extend a little bit here. So the mixed level equation has 2 primary components. These are the regression components and 2 primary components. So the regression components and then the error components. The regression components are basically the averages of the intercept and slope. These are what we call fixed effects. And the error components, those are the kind of the deviations that we talked about around these average estimated values. And these are what are called random effects, okay? Now, if you understand this, it'll be easy to transition into doing this from an SEM perspective, because the same principles, right, that exist in mixed level models are the same in within the SEM framework. Now, in growth modeling, which is kind of taking that same problem that we just presented from a mixed hierarchical perspective to an SEM perspective, instead of having manifest variables, right, observed variables, here what we want to do is estimate some trajectory, right? We have, this is at time 1, estimated to observed at time 1, observed at time 2, observed at time 3, observed at time 4. And we think that this trajectory, at least based on this graph that you see here, is a linear trajectory. As we said, a linear trajectory, a line, is usually defined by two things: where it starts and how it moves, right? So these are the intercept, the starting point, and the slope. So now you can see that how this resembles the mixed modeling formulation. But based on this kind of visualization here, you also see that this also resembles a factor analysis type modeling that we looked at before, right? This is a unmeasured variable. These are measured variables, except instead of these being different variables, these are the same variables measured at different time points. So I can reformulate things and argue that the trajectory, right, can be summarized by two elements: where you start, which is the intercept, latent value, and how you move over time, and that is the slope, which is also a latent value. As long as I have sufficient pieces of information, I can change kind of the structure of this trajectory. So if I have 3 measured time points, then I can only fit a linear model. But if I have more time points, I can have more complex structures. So if I have 4 time points, I can add 1 more latent factor and assume that or test whether there's a quadratic effect. If I have more time points, I can probably test more complicated parametric structures and even non-parametric structures. But the principle is the same. What we're interested in is where you start, which we assume is a latent factor that has a certain distribution, that distribution could be inferred from these manifest. And we assume that there's a slope, a trajectory of change that has an average and some kind of a deviation around it that can also have a certain distribution, which is what we call the slope. The idea about the link between the gross SEM and CFA makes sense, hopefully, at this point. The implementation is slightly different, however. Remember, in CFA, what we've done is each one of these, right, were left to be, what we did is we anchored around one measure. We chose what that measure was, just to make sure that the latent factor has the same metric of it. And then we left the other loadings to be estimated. In a longitudinal SEM, on the other hand, we have to impose, right, what the structure of these loadings look like. So for the intercept, what we do is we fix the loadings to 1. And then by that, what we're basically doing is saying that the mean value of this, right, is based on the mean value of these manifest. And then for the slope, we also impose a certain structure on how things are moving, the units of time increase that we want to get. So this formulation that you see here, right, it's 0, right, that's time 0. This is time 1, this is time 2, this is time 3. Now here we have to be careful about how we do that, primarily because if the times are not equidistant, then we have to make changes to how we kind of set these loadings. But also, if we're not looking at just 1 year move, so if we're looking at 2 years of movement, etc., then we have to be careful in terms of how to set this. Or if we set it as 0, 1, 2, 3, we have to make adjustments once we kind of estimate the model. The model, you know, once you do it, the mathematics are pretty straightforward. it allows you to spread, to also estimate what are called spread around these two values, the intercept and the slope, right? So the average estimate for the intercept and for the slope are what are called fixed effects. And then the deviations around the slope and the intercept, these are random effects, right? Again, think back on the MLM formulation that we talked about. We estimate one average slope, we estimate one average intercept, and then we calculate these deviations in intercepts and slopes around those averages, and those are the random effects, same as with what we're seeing here. The variances in baseline values and trajectories, as I just mentioned, these are called the random effects. And you know, we can potentially explain these random deviations by making adjustments to how we fit the model. So we can add time invariant covariates and see if that's going to help shrink the deviations around the mean values. We can also add time varying covariates and see the impact of that on potentially deviations around the slope. I'm going to skip this one here. This is just to show you that you can also, while you can force kind of the association between where you start and how you move to be zero, it's probably not wise to do so, because in many instances where you start is also associated with how you move over time. So that also could be estimated in SEM, like it is estimated with MLM. This is the covariation between the intercept and the slope. This is just to show you the different structures of data that we use when we're doing mixed modeling. Basically, the structure of the data is long, right? You just stack up the time elements in hierarchical modeling, whereas in SEM, a growth curve modeling, what you do is you use wide data rather than long data. This obviously has implications to how you fit the model. But let me just do an example here, just to potentially clarify what we're trying to estimate and what happens once you adjust for covariates. So in this particular example, T1 through T5 are TIC scores. These are, again, the sum of cognitive scores based on two measures of memory, backward count, I think, and mental status. They range from 0 to 27, measured at in 2006, 2008, 2010, 2012, and 2014. This was estimated using individuals that entered the data into 2006. They have 2006 weights, and based on the Leave Behind questionnaire and the HRS. What we did here is we set the loadings for the intercept, this, and this to 1, and then the slope loadings from 0 to 4. Now, again, here I made an executive judgment to do it 0 to 4 rather than 0 to 8, but the way I'm going to interpret the beta, right, the fixed effect is change every 2 years rather than change every year. But potentially you can change the way you kind of parameterize this, so you can go 0, 2, 4, 6, 8, and then it could be then the beta estimated would be basically the split in half, and that becomes the yearly change in these values, right? This is how you enter it in R. This is Lavaan in this particular case, the package that was used, and this is what you get by estimating this, what's called an unconditional model, right? You get two things, as we mentioned. We get the fixed effects, so these are the averages for the intercept and the slope, average where you start versus average how you move. And you get also deviations around the intercept and the slope. So we know here that the average start is 16.5, right? And the average movement over 2 years is about 0.385 points on a 0 to 27 scale. Both of these are significant. The p-value is less than 0.05. And we know that there is a relatively large set of deviations, 9.4, right, in the metric of the TICs around the intercept and about 0.14 around the slope. Our job then is to try to explain these deviations, add things to the model to try to explain deviations around these, but also to try to connect, right? Do some fixed effects analysis, regression analysis to connect a set of covariates to these intercepts and slopes. These are just basically interpreted like you interpret any other regression. Let's say if you have sex in the model or race ethnicity in the model, and then you get a beta of sex on the intercept, that beta would be how much the intercept would change by moving from males to females, or however you kind of entered that into the model. Let me see. I'm just, what this does here is it complicates the unconditional model that we talked about before by adding one covariate. This is X1. Again, the one thing that I want to emphasize is that this and this could be interpreted just as you would interpret any regression coefficient. This is the math behind that, so I'm not going to spend any time. Let me just move from kind of that the set of findings that I showed before to show you what this looks like. So now we've entered this X1 into the model. The intercept and the slope stayed about the same because this was centered. But what we see here is a change in, I think this is education that was entered here. What you see here is a change in the variance estimate for the intercept. So adding this X1, adding this covariate into the model, changed the deviation, reduced the deviations around the intercept from 9.4 to 8.8. So that has a contributing factor in explaining some of the across individual differences in where they start. Let me see. Let me just move to one last one. This is, again, the fixed effects. So what I showed you before is how you kind of interpret the random effects. What I'm showing here is how you interpret the fixed effect. So this is the effect of X1 on I and X1 on S. You can interpret this in the original metric of X, or you can just focus on the standardized value. So the standardized value would tell you that one standard deviation increase in X1 would lead to about a quarter of a standard deviation increase in the intercept, and a one standard deviation increase in X1 would lead to about 0.035 standard deviations decrease in the slope of cognition. You can complicate this model more by adding time varying covariates. I don't think we have enough time to kind of go into this, but it's a relatively straightforward extension. What you have to notice here is that these time varying covariates are not regressed on the intercept and the slope, they're rather regressed on the time manifests, right? So, and that's just the way that SEMs work with time varying covariates. The interpretation is relatively the same. You look at the random effects, you see how much was explained in these random effects, both for the intercept and the slope. You also try to look at the beta coefficients, and these are the fixed effects, linking each one of these covariates, whether it's time invariant or time varying, to the intercept and the slope estimates. There are several complications to this. So this is just scratching the surface. I didn't account for survey design, at least didn't talk about survey design. I didn't say anything about missing data. The complications introduced by not having equally spaced observations. For those of you that work with the HRS, you know that it's every 2 years, but potentially you can have measurements that are not equally distanced. You can have cohorts effects, which we didn't address here, individually varying time points. That's also a complication of kind of the data collection mechanism, and then non-normal manifest variables. So most of the things that we talked about assume normality and multivariate normality. I think I did pretty good on time. These are some books that you can read. What I try to do is give you a combination of some theoretical stuff that is really digestible in terms of English to math. Newsom's book on longitudinal model is fantastic. Rex Klein is obviously a classic. And then I gave you some books that you can take a look at that includes a lot of kind of translational things. So this is what the substance is. This is how you go from the substance to actually fitting models in R. I know some of you use Stata, so I'm going to try to add a few references for those of you that do that. And I will stop here. Suffice it to say that this is probably 3 different courses, each stretching a semester, but at least you have an idea of what these methodologies are and how potentially you can employ them in some of the work that you're doing. That's a huge silence.
Excellent.
Yeah.
Excellent.
Hopefully, you know, I didn't give you a headache talking for about an hour.
I think it's very, it's a lot, but I love, you know, it's just variations on the same theme, you know, and I think that just sort of that emphasis on you can do this, it's the, and you know, I know we're out of time, but like, I would encourage all of our scholars to just reflect on what this means for your work. You can either reach out to Wasim directly or bring this up during our monthly Muckwar meetings, right? You know, we had this seminar series and I was thinking about how this might relate to my work, right? So just, this is an ongoing thing. And at least in my own experience as a learner, applying it is the best way to learn it. So, I mean, when I wanted to learn multi-level modeling, I was like, all right, I'm gonna do a paper using that. Like literally, like that was the goal. It wasn't just to kind of like learn in an abstract way. And so if this is something that you are ready to use in your work right now, go for it. If it's something that might not be, you know, I wouldn't sort of spend a lot of time trying to learn it in an abstract way until you're ready to apply it. But then you've got these resources there when that time comes.
Thank you, Bree. So the one thing that I would add is that, and I know we're at time, is any one of those, we can do something that is kind of more zeroing in on that sub technique. This is just to kind of give you what's available, and that it's really not as complex as you might think it is, at least from an applied perspective, right? And so then, you know, we either on an individual basis or we can do other kind of 1 hour seminars on this. We can deal with each one of those techniques separately.
Thank you, Wasim.
All right.
Thank you, everybody. Have a
Thank
great
you
one.
all.
Bye.
Bye-bye.
Thank you. Thank you.
Bye-bye.